Hi, welcome to another video. So I've been asked if I could do a quick CAN tutorial. Now I used to work for an Iveco Ford dealer. Incidentally, they've been taken over by Iveco, so they can't be too bad. So I know a bit about CAN communications on vehicles, but today I'm looking at CAN communication via a microcontroller. So what I've done, cut up an old Ethernet cable. See, that's the old plug there. And you'll know inside, or you might know inside, there's 4 pairs of twisted wires. So CAN communication between one node and another, what they call the microcontroller's nodes, or the modules. Between one node and another, you'll have a twisted pair. And here, to mimic Iveco's wiring, I've used CAN high is green and CAN low is white, although this has a green trace on it. So that's the little transceiver down here. That converts the signals from the microcontroller into a differential pair. Now if you're confused already, don't worry, I'll show you the drawing and break it down for you. I've also set the CAN up on the scope, looking at the ID and data, that sort of stuff, and I'll get back to that once I've gone through the drawings. Because I haven't got a CAN receiver or no transceiver set up at the end of this wire, I've just got a simple 120 ohm resistor, or a couple of resistors to make up 120 ohm. Now in this instance, that 120 ohms isn't quite right, it's overloading the CAN line, but it just illustrates what you're meant to do. 120 ohm termination resistor at the beginning and the end of the CAN line. Right, so I've been working with Windows Paint, that's all I have to draw images. So you can see JB's CAN Basics, and that's today's date. So there's 2 types of CAN essentially, 2 standards. CAN 2.0A standard 11-bit identifier, and then CAN 2B extended 29-bit identifier. Now that identifier is not only the identification of the module sending the signal, it's also, within the code, it's like a priority bit, and which message, if you've got 2 or 3 modules trying to send a message, which message is going to win and come through and be answered. So more about that later. So this CAN 2B is essentially what's used on vehicles. And then you've got 2 speed standards. ISO 11892, it's a high speed up to 1 megabits, and the ISO 11983, it's a low speed up to 125 kilobits. So that's what I'm going to be looking at today, the lower speed, using Microelectronica's CAN sample for the EasyPic Fusion version 7, which has an onboard CAN transceiver. I've had a look at the MikroC code as well, and the code is similar, and I think I've found some errors why the program doesn't seem to be working correctly. It seems to be using this lower speed standard, but some of the code is using this extended 29-bit identifier, and my scope just wouldn't synchronize with it. So if you're running at 1 megabits per second, high speed up to 40 meters in length, which isn't necessarily enough for a load of wire on a long coach or long truck. And then you've got the slower 125 kilobits per second low speed, which runs up to 500 meters. You need to know a small bit about electronics to understand this distance. Hopefully you might appreciate, if you're running a wire over 40 meters, apart from the resistance in the wire, it's going to take time for a signal to turn on and then back off. So that's why they go for these 2 speed standards. So if you're new to CAN communications, a controller area network, and you want to know why they adopted the CAN method over regular on-off signals, digital on-off signals, if you look at this example here, so using a 3.3 volt microcontroller, or 3.5 volt microcontroller, you can see to send a 1 simply turns on, then there's a gap, that would be like a 0, and then you send another 1. But if that's on a vehicle or some industrial plant, something like that, you might get some EMI or ESD interference, just for, maybe that's a nanosecond or microsecond, but that's enough to turn something on or off. So EMI, electromagnetic interference, ESD, which is electrostatic discharge, and there's loads of other bits of interference you can get there, just the two common ones. So on a vehicle running high speed frequencies, you can't afford to have communication, say from an engine to a gearbox. You can't afford to have errors and have a 1 where there's no 1. 1 being on and 0 being off. So to convert these simple on and off times, CAN adopts the differential method. Green is the CAN high and the lighter green is the CAN low. When nothing's being transmitted on the CAN line, both the CAN high and CAN low will sit around 2.5 volts. You put a multimeter on it and that's what you measure. When they start transmitting, the CAN high goes high up to 3.5 volts or whatever supply is running at, and then CAN low comes down to 0 volts. And the receiving node will look at the differential between the two voltages. What's slightly confusing is when nothing's being transmitted, we've got the 2.5 volts. When it becomes active, you can see here that CAN high is high, CAN low is low. That actually gives us a 0, so that's a nothing. And when nothing is being transmitted, we've got a 1. So you've got to get your head around that first of all. Normally that would be a 1 and then that would be a 0, but on a CAN line it's back to front, inverted. So hopefully you know why Mr. Bosch came away from this method of communication, which on a vehicle is pretty unreliable, and he adopted and designed or invented this method, and it's very reliable. So the only other thing you need to know essentially about CAN for the basics is, so that's a 1 when nothing's being transmitted, both lines are at 2.5 volts, and when both lines are active, so CAN high is high, CAN low is low, they'll never be in between. They'll either be at 1 or nothing, unless you've got a fault on the CAN line. If, say for example, the CAN low was short to ground or the CAN high is short to ground, then you've got an error on the CAN line. So this 0 is a dominant bit, and this 1 is a recessive bit. So to understand the meaning of these dominant and recessive bits, you need to look more into CAN, what it is and why it is. So some of you might be familiar with vehicles, and maybe you're looking at an instrument cluster and you've got loads of nodes reporting error messages to the instrument cluster, but they all can't communicate at once. So let's say we've got an engine overheating and the rear light controller has reported a side light failure. Obviously a side light failure compared to an engine overheating isn't very important. So, but if they both start transmitting at once, something's got to give. You can't read two messages at once, not on one CAN line. So if you look here, remember I said the dominant bit is a 0 and the recessive bit is a 1. So that's a 1, that's a 0. So 0, 0, 0, 0, 0, 0, 0, 0, and then a 1. So this is where we use the word arbitration. So the receiving node looks at the data coming in, say for example on this line for the engine data, and in this case it's the engine's overheating, so there'd be relevant data to signify that. And in this side light failure, for example, it's going to transmit a certain hex code to say we've got a side light failure. So this engine is transmitting dominant bits here, 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 but all of a sudden the side light node or the light control module starts transmitting these dominant bits, but because the message is less important, it's got a recessive bit here. So it's trying to write a 1, but there's already a dominant 0 on the line. So actually the side light controller or the lighting controller would actually stop there because the engine has got a dominant bit. That's more dominant than a 1. So the lighting controller would stop. So you can see here I've got a note the engine wins the arbitration with the dominant bit. The lighting controller would stop here because there is a dominant bit on the line. It would then send the message later. Now obviously today I'm only looking at a transmitter. I haven't got a receiver, but if I did have a receiver, I'd still only have a transmitter and receiver, no third node to come along and try and interrupt. So maybe I'll buy 2 transceivers and give this a go, give this an example, give you a demonstration of the dominant and recessive bits when 2 units are trying to communicate. So the final thing about this dominant bit and recessive bit, obviously if you've got a vehicle manufacturer, Iveco for example, they'll have all their nodes, maybe 12, 15 nodes, gearbox, doors, engine, ABS brakes, that sort of stuff, all these different nodes on the vehicle. They're not going to design a lighting control module to have higher priority over an engine module. And the engine's got to talk to the gearbox, that sort of stuff, so a lighting module and the 11-bit identification and fault code is always going to come second to the engine overheating. So when they're designing the microcontrollers and programming them, the 11-bit or 29-bit identification is always going to have a recessive bit sooner than the engine. So today I'm using the 11-bit identifier example. That's what I programmed on the microcontroller, and I can show you all this on the scope. So we've got a start bit, and now with this start bit, every transition from 0 or from 1 to 0, the receiving node will adjust its clock and synchronize on these leading edges. So we're only transmitting the data, and each node has its internal clock, synchronizes here. I'm not sure if it does it on every edge or every 5th edge, but it certainly synchronizes on these edges certainly at the start bit. And in the example today we've got an 11-bit identifier. So we've got 0, 0, 0, 0, zeros. Remember that's the dominant bit. So that's a string of zeros. And we've got a slot there for remote transmission. Then we've got an ID extension slot, then a reserved slot, and we've got a data length code, which is 4 bits long. Then we've got 15 bits, so I've shortened this down. We've got 15 bits for CRC check, so cyclic redundancy check, and that compares the bits sent with the bits received, and then those 2 figures should match with the receiver's CRC check. And you can have errors in the CRC check. The transmitter could send 1 code or 2 hexadecimal bits for these 15 bits, and the receiver could decide the CRC check should be a different value. So you get the CRC check error. Then you've got a CRC delimiter. Then you've got an acknowledge bit, acknowledge delimiter, and then just above, end of frame, 7 consecutive bits. So in the standard frame you see all those bits. In the extended frame the identifier isn't going to have 11 bits, it's going to have 29, so it's obviously going to be longer. So this end of frame, 7 consecutive bits, this is quite important, and I'll show you why. Now to confuse you, there's a start bit again, so 1, 2, 3, 4, 5, 6, 7. Only trouble is, during the frame you can't have more than 5 consecutive bits of the same value, and you see here, and I'll show you on the scope with my ID code, you see here, look, these are all zeros, 0, 0, 0, 0, 0. This isn't allowed in the CAN communication. So what happens, we've still got the start bit, which is obviously dominant. Then we've got the 1, 2, 3, 4, 5, and then what the CAN does, it puts a stuff bit. It stuffs the opposite value. It's an odd word for something so technical. The CAN protocol, if there was another 1 here, because that would be the 6th consecutive bit of the same value, the CAN protocol says that's got to be removed and inverted. So if we had a string of 1s, so it would be nothing, 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 the stuff bit would be a dominant bit. But in this case, because I had 0s here, it's putting a 1 there. Now in the frame, the stuff bit isn't counted. So we've got bit 4, bit 5, a stuff bit, and then bit 6, bit 7, bit 8, and so on and so forth. And I can show you this on the scope as well. So here's an example of a CAN setup. So we've got 3 CAN nodes, all connected to CAN high and CAN low, and you saw the resistors on the end of my network. At the start network, you've got a 120 ohm resistor, and at the end, the last node, you'll have a 120 ohm resistor. This resistor corrects the voltages on the CAN line. Without it, I can possibly show you later, when the CAN line is turning from dominant to recessive, so when it's turning from on to off, without this resistor, the off time will actually slow down and it will upset the timing on the network. So these will influence the on and off times, or the rising edge and falling edge. And as you can see, they've all got their internal oscillators and they all synchronize with the bits coming in. So this is the last of my notes. So finally, a transmitter can report bit error and acknowledgement errors, and the receiver can report form errors, cyclic redundancy check errors, and stuff errors. And this is a note in case some vehicle technicians are watching. So I worked on Ivecos for many years looking at CAN errors. Generally it was wiring issues. There were the odd modules that had internal errors. And if Iveco are saying, well, what? Their gearshift module on their Stralis, for example, gearshift module would send communication, would send CAN details to the gearbox and the engine, tell the engine and the gearbox what gear to select, and vice versa. And the gear shift lever started to fail on many vehicles. On a vehicle, if one node keeps on reporting an error on the CAN and no other node does, it must be faulty or have dodgy wiring. Errors on the vehicle modules are counted. One can read what module is reporting what error, and that's done with a laptop. A full register once flagged a CAN fault on Ivecos, to name but one. If you erase the fault memory without finding the error, the fault memory will come back to haunt you. Right, let's turn to some code. So before I start, taken from MikroChip's Pic32 CAN datasheet, this Pic32 controller area network, CAN, module implements the CAN specification 2.0b. And you remember from the drawing, 2.0b is the extended 29-bit identifier. So if I didn't mention, this is compliments of Microelectronica. It's their example software on their website. And this, I'm hoping to answer the question I was asked. This code, I've looked at MikroC Pro for PIC, which hasn't got the onboard CAN. You have to use the CAN SPI module. But I looked at the code and it's very similar, very few differences. So I think Microelectronica has simplified this. They've got various flags. So you can see CAN init flags, CAN send flags, and CAN receive flags. Now if you look at MikroChip's datasheet, those flags have specific values in the registers, but I think Microelectronica have simplified it for the end user. So you can see receive data length, that's a receive transmit, so we're transmitting 8 bits, message received, and this is what's confusing for me. So constant unsigned long, ID first, so remember 2.0b has got a 29-bit identifier. Now Microelectronica's first ID is something like 12111. So if we pull up the calculator, go to programmer view, so 12111 binary, we have that. So it's 1 So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bits. So presumably the code is just going to put a string of zeros here, followed by these last 14 bits. Now to simplify this, and so that we get the ID up on the scope, I've deleted this because my scope wouldn't synchronize with it. I've deleted that and put 2047. So pull the calculator up again, look, programmer, decimal, 2047, convert that to binary. We've got 11 bits there. Let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That satisfies our 11-bit identifier in the standard frame, not extended. You remember I said we can't have 5 consecutive bits of the same value, so I'll show you on the scope that stuff bit. So now that binary representation to hexadecimal is 7FF, so that's the ID I'd expect to see on the scope. So in case you're wondering, this is Keysight Oscilloscope, Keysight Technologies, formerly Agilent Technologies. It's the InfiniVision DSOX 2012A, but I've purchased the serial decode licenses. So while I'm on this screenshot, this is the can high in yellow and can low is in green. So if I now pull in one whole sequence, remember I said the ID we're looking for 7FF, which is our decimal 2047 I sent. So that's the correct identification. So we've got a data length code of 1, so we're just sending 8 bits or 1 byte. And I'll show you in the code, we've got FF is our data, and then at the end this is our CRC, cyclic redundancy check. Zoomed you in a bit. So there's our correct ID, data length code of 1. There's our data we are sending, so it's FF or 255, and there's our cyclic redundancy check 7A15, which is actually 15 bits. And what we haven't got, because my transceiver isn't connected to anything, we've got no acknowledge at the end. And because I haven't got a receiver, this data is being transmitted, not acknowledged, so it can't send the next bit of data. So I'm synchronizing this scope on the ID and data field, so that's the time, 345.8 microseconds. That's our ID, 7FF. Type is data, so we've got one bit of data being transmitted, which is the FF, and that's our CRC 7A15. And then we've got a form error because we've got no acknowledge. So here we have the can ID, a string of 1s. So 4 plus 4 plus 3. So that's our 11 bits. That's our 11-bit ID. And over on the right hand side you can see that's converted to hex, so 7FF. So that's the data being transmitted from my transceiver, from my microcontroller. But what I wanted to show you, so we're sending all the 1s. So 1s are recessive bits, so there will be, like this gap here between the 2 bits of data, all the 1s will be recessive bits, so there'll be nothing. So if I go to the start of the frame and expand this out, so if you get a rough idea how wide this start of frame is, so it's roughly the width of this coffee stirrer. So that's the start of the frame, and we're sending a string of 1s, and I said you can't have more than 5 consecutive bits of the same value. So look, 1, 2, 3, 4, that gap's small, so but roughly that's 5 1s, and that's a stuff bit. Then we've got 5 more 1s. So if I change the time base on this scope to fine, press this button, now on fine. So if I expand this out, So you can now see the start bit is equal to 1 division. So that's the start. Then we're sending the string of ones down here. So look, 1, 2, 3, 4, 5. If I didn't send a 1, all of a sudden we've got a 0 there. So that's the stuff bit. So that's not counted in the frame. Nevertheless, it's in there. So there's a 1, 1, 1, 1, 1 stuff bit. Followed by 1, 1, 1, 1, 1. Another stuff bit. But that stuff bit's slightly narrow, I think. Or has come in slightly early. And then there's our last one. So if I now change this ID, 11-bit ID, to 1024, pull up the calculator again, as proof, so I'm in program view, so cancel that. So we're sending a decimal ID here, so 1024, convert that to binary down here. You can see now we're sending a 1 followed by 10 zeros, and in hexadecimal we've got 400. So let me program that and show you on the scope. Right, so this is that 1024, and remember from the calculator, type it in. 1024 in decimal is hexadecimal 400. There's our data length code, we're still transmitting 1 byte. There's our data, and there's the CRC checksum. So previously I'd sent all the ones in the CAN ID, and now I've sent a 1 followed by 10 zeros. So remember 1024, put it on the calculator, convert it to binary. So there's 4 zeros plus 4's 8, 9, 10, 11. So there's our 11-bit ID. Over here, that's converted to hexadecimal 400. So remember previously, our identification, they were all recessive bits. Now we've got dominant bits because we're transmitting zeros. If I press the trigger, get it up down here. See, we're sending the zeros. So there's our start bit. There's the 1. Then we're expecting 10 more zeros. So we've got 1, 2, 3, 4, 5. Then the stuff bit, and as before, it's come in slightly early. I'll have to look into this timing issue. That's the stuff bit. So 1, 2, 3, 4, 5 zeros. A stuff bit, and then 6, 7, 8, 9, 10, and stuff bit again slightly early, and that's the whole code. So hopefully you can understand now. So that's our ID, data length code. We're only sending 1 bit. That's the ID I'm sending, and that's the checksum. So if I change this FF, so today is the 18th of January, so I'll send an 18 here. Well, I've just reprogrammed it, and then we've got an 18. I've actually said hex 18. So hopefully this ID now makes sense. As for the second ID, don't ask, no idea. Not had time to look into it. But these are the buffers for the internal memory of the microcontroller, depending on what's being transmitted or received. These bits here set up the clock, that sort of stuff. This one here, for example, BRP, is a baud rate prescaler. I'm not sure why they're set as constant unsigned ints, because they are registers in the microcontroller, and I'd normally expect microelectronica to have these registers set. I guess it's keeping it simple. So you can see sampled once. There's a question mark here. So this is obviously the CAN config extended message. So I'm only sending 1 bit of data and only 11 bits for the identifier, not the extended 29 bits. So I don't know in this program, MikroC Pro for Pic32 and the MikroC Pro, if the error is in this part. So you can see match on message types, filter off, that's the initialization. So I put this char in, I was just messing about. So this is obviously the analog to digital converter register. If you're not familiar, look at my other videos, I've done one on there. This is port B, just to bring on all the LEDs when it's counting up. I think this is the simplified version done by Microelectronica for the flags, because if you type in various commands, various registers, they do come up in this MikroC Pro for Pic32. So just so you know what I'm talking about, let's say for example you've got a CAN timer overflow interrupt flag bit. So that register in the Pic32 is CT MR and then IF for interrupt flag. Now you can see the red line's gone, so this 32-bit compiler recognises that register, and if you hit Control Space, as with any of the other compilers by Microelectronica, it gives you the bits and what you can do with them. So I'll delete this. So I think these various flags, the send and receive flags, are just simplifying the code. So what I've changed, and you might find your MikroC Pro for Pic compiler might be the same, is this can transmit extended frame and can transmit no return frame. So it's this extended frame. Now my scope would not synchronize when this was enabled, no matter how many bits I put in the ID, whether it's 11 or 29 for the extended, which this Pic32 is meant to run on the extended frame, so I can see why Microelectronica put this in. My scope has the facility to accept an extended frame, but no matter what I did with this part of the code in here, it wouldn't work. So I removed this bit out. Have to leave this bit in there and put semicolon. You can actually have can transmit standard frame. So these are the various configurations. So can first in first out buffer, so that's a receive buffer, transmit buffer, that sort of stuff. Have a look at the data sheet if you're interested. There's can masks, normal mode, that sort of stuff, and this is what I just added just now. So that's a receive transmit data. The first item of data defined by naught, so I've set it to hex 18 because it's the 18th today, and then that's it. Can to write, so it's the first, so ID first, and the receive transmit data, which is that 18. Then that's 1 byte I'm sending, and then it's sending the can send flags, which I say are simplified in this example. So that's what's happening here today. Simple can to write. So in their while one loop, if I had the receiver connected, it's looking for the received message, so it's can to read, so it's and the receive ID, so it's making sure the ID received from the second node is what we're looking for. Then it's accepting the data, and the data length has got to be correct, defined at the beginning of the software, and then can receive flags, so it's and for the bits of the receive flags. So if the RxID is equal to the ID second, so now I know what the ID second, that's number 3. Presumably, I've not looked at the other code, when you program the second node, the ID is number 3. So if the received ID is number 3 and a message received, which is a variable, port B LEDs turn on, equivalent to the data received, then the receive transmit data is incremented by 1, so this 0 in here would go to a 1 for example, and then we've got a 5 millisecond delay. Then we're going to rewrite back to the second node this ID from the transmitter, so the ID first, RxTX data, which will have been incremented by 1, so this 18 would become 19, for example. We're sending 1 bit of data and can send flags, but because I haven't got a second node connected to this transmitter, I can't receive anything, and I'm not getting an acknowledge either. So there's our can high, can low, and various data bits. Hopefully it all makes sense. If you expected a short video, you must be balmy. Hope you didn't expect a short video, because you can't discuss not half of this can in 5 minutes. You'd be left with loads of questions, so I've gone into a fair bit of detail, but not too much. Hopefully you've got a good understanding. Thank you for watching.